Okay, so let's start. So next presentation is Pitoiset. He was a GSoC student this year and the previous year, and he's been working on exposing NVIDIA's performance counters on Nouveau. So we had to do a reverse engineering and then implementation work. So, Samuel.
So hello everyone. My name is Samuel Pitoiset. I did 2 Google Summer of Code for the Nouveau project. And today I will talk about NVIDIA performance counters and how to expose them to the user space. So I will start with a little introduction, what performance counters are exposed by NVIDIA and by Nouveau. And after I will talk about my proposal for this Google Summer of Code. So performance counters are blocks in modern processors that monitor their activity. They count low-level hardware events such as cache hits or cache misses. Why performance counters are used? So basically they are used to find the bottlenecks of 3D and GPU applications and to dynamically adjust the performance level based on the usage of the GPU. So NVIDIA exposes 2 kind of counters, so compute counters for GPU applications, which are exposed by kubTI, the CUDA profiling tools interface, and graphics counters for 3D applications, which are exposed by PerfKit, but only on Windows. What about Nouveau? So for Nouveau, compute counters for Fermi and Kepler are exposed to the user space by the Gallium HUD. The Kepler support by Christophe Bumiller, Kalim, and Fermi support was added by myself during my first Google Summer of Code project. But many performance counters left to be exposed, like graphics counters. So before exposing graphics counter, we first need to reverse engineer them. So we have to use PerfKit on Windows 7. I did this work during the 2 GSoC projects. And this year, my proposal was to expose graphics counters for the Tesla family. So basically, we write and design a kernel interface in Nouveau DRM to add the support in mesa for the Gallium HUD and to implement 2 performance counters APIs, so GL AMD performance monitor and Nouveau PerfKit, which will be a Linux version of NVIDIA PerfKit for Nouveau. So the benefit for the community is to help developers to find bottlenecks in their 3D applications. So now I will talk about performance counters engine. So pcounter contains most of the performance counters. Pcounter is made of several identical hardware units called domains. For each domain, we have 256 input signals. And all of these input signals are from all over the card. So pcounter is used to sample global counters. And performance counters are tied to a clock domain. So the signal is just a binary value. If you want to monitor the number of cache hits, the signal is at 1 when cache hit has happened, and at 0 when there are no cache hits. And but NVIDIA has thousands of signals, so we have to use some multiplexers. So because it's really expensive to have 1 counter for every possible signal, we use a multiplexer. So the idea is to combine 4 signals using a function that goes in a truth table. And we get a macro, something like macro information. For each domain, we have 4 independent counters and 1 counter for the number of cycles, which is the clock domain. And this is for pcounter, so for global counters, but we have also other counters. So we have pair context counters or multi-processor counters. They are pair channel, and they are located in pgraph, which is the main engine for OpenGL and OpenCL. MP counters are more accurate than global context switch. We also have the same logic as pcounter, the same truth table, and sometimes some MP counters share some multiplexer with pcounter. And currently, we have to launch an OpenCL kernel to read them because MP counters are programmed by the command stream of the GPU. So pcounter, the signals, what do we know? So for MP counters, all GPU signals for Tesla, Fermi, and Kepler are reversed. This work has been done by Christophe Bumiller and myself. For global counters, so performance counter for pcounter, they are very chipset dependent. So for example, if we find a signal for one card, it may be different for the next one. Actually, very likely different. But currently, we know more than 200 signals for the Tesla family. This work has been done by Martin Kosielnicki, MWK, and myself. And now, what about graphics counters? So almost all exposed by perfkits are reversed and documented, and but some per context counters still need to be reversed. These MP counters are mostly for the shader. So now I will explain you the reverse engineering process. So reverse engineering on Windows is very painful, but 3D signals are only exposed by perfkit, so we have to deal with Windows. But I couldn't use the NV tool, section of NVIDIA related tools and documentations, because NV tools is based on libPCI access, and that library was not supported by Windows. So to deal with this problem, I added libPCI access support for Windows and Cygwin. So now we can use NV tools on Windows, but we still don't have MMIO traces, and we don't have Valgrind MMT. But anyway, we can start the reverse engineering process. So how does it work? Basically, we have to configure the hardware perfkit on Windows 7. After, we can dump the configuration with some tools of NV tools. So, but sometimes some multiplexers are very difficult to find, so we have to dump a lot of registers in pgraph. After, we can try to regenerate the same results by polling the counters on W7. And the final step is to reproduce the configuration on Nouveau. But we have around 50 graphics counters for the Tesla family and 14 different chipsets. So we have to find the graphic counter for each chipset. But in order to help me in the reverse engineering process, I modified the OpenGL application provided by perfkit, which can be used for monitoring performance counters. So now these applications can automatically configure and export the configuration of performance counters. So this is a screenshot of the OpenGL application. So basically we have some options. We can select the render mode. Model, we have cube, a bunny, and a dragon, and on the bottom on the right, we can see the evolution of the performance counters along the time. So now I will explain the kernel interface I implemented during this GSoC project. So why do we need a kernel interface? Because global counters have to be programmed through MMIO. So only root or the kernel can, and what the interface has to do, so the interface has to set up the configuration of counters, and to poll the counters, and to expose counters data to the user space, which is called the readout. But we also have to synchronizing these different operations on the GPU. So for synchronizing operations, on the CPU we have IOCTL, then on the GPU we have software methods. So software methods is a command stream of the GPU context. So basically, when the software method is invoked, the GPU is paused, and the CPU gets an IRQ and invokes the command inside an interrupt context. So software methods are tied to the command stream of the GPU, and they are very useful for synchronizing operations with the GPU. And for the kernel interface, we use some software methods. So this is a very simple overview of the kernel interface for Mesa. So we have different steps. The first one is to allocate a performance counter object inside the kernel. This is done with an IOCTL. And after we get the handle of the object, which is something like a unique ID. And after we have 3 software methods, so number 3, 4, and 5. So after we can start a monitoring session. And then we can, for example, render a fresh GPU. After we have to stop the monitoring session. Then the step number 5, we have to expose the value of the counters to the user space. So basically, the kernel writes data to a notifier buffer object, which is a ring buffer, and Mesa can read back them. So for the notifier buffer object, it's just a buffer which is automatically allocated by the kernel when Mesa creates a channel. So this buffer has to be mapped from the user space, and after it can be accessible from the user space and the kernel space. Now what happens from the GPU? So when we start a monitoring session, Nouveau writes the configuration of the counters to pcounter, and after it resets all the counters because we want to start all the counters at exactly the same time. And when the end monitoring command is invoked by Nouveau, Nouveau polls all the counters and store the value of all the counters and the number of cycles. And after he writes a fence ID, which is a sequence number, and it writes the value of the counter to the notifier buffer object. But this kernel interface is also able to monitor different performance counters at the same time. So we have to synchronize different queries which are sent from the user space. So basically, it sends a query ID, so the sequence number, to read out the results. And this sequence number is written at the offset 0 inside the ring buffer. So it's easy to check if we have the result. The ring buffer queues up 8 queries or frames, so like the HUD. So this avoids stalling the common submission. So this figure, the offset 0, we have the sequence number. We can store 8 queries, and for each performance counter, we store its counter and its value and and the number of cycles. So now performance counters are exposed by the kernel interface to Mesa and to the Gallium HUD. But we want to have more performance counters API for the user space. So we have some proprietary API, like perfkit for Windows and kubeti and GL AMD performance monitor for Windows and Linux. But in open source, we only have the Gallium HUD for exposing performance counters of Nouveau. So during my GSoC project, I also implemented GL AMD performance monitor as a Gallium state tracker. So the patches are available for some drivers, but currently the patch set is pending because I'm waiting to complete the kernel interface before to rebase and to update the code. Now about Nouveau perfkit. So it will be a Linux Nouveau version of NVIDIA perfkit. Nouveau perfkit is also implemented as a Gallium state tracker like VDPO. Nouveau PerfKit will expose both compute and graphics counters, and I will use the same interface as NVIDIA PerfKit, so it will be really easy to port an application for Windows to Linux. So this is a general overview of the graphics stack with Mesa. So we have some state trackers. In the OpenGL state tracker, we have the GL AMD Performance extension, and Nouveau PerfKit as a new gallium state tracker. So currently, only Nouveau expose its performance counters to Nouveau PerfKit. But since Nouveau PerfKit is built on top of Gallium as a Gallium state tracker, some other drivers could also expose their performance counters through Nouveau PerfKit. So now the current status. So all 3D global counters for family are reversed and documented. The kernel interface and the Mesa implementation is on the way. I hope to see the code in Linux 3.20 or 3.21. The GL AMD Performance Monitor extension is almost done. And in my to-do list, I have some interesting stuff. So I will continue to implement Nouveau PerfKit as a gallium state tracker. I will try to reverse engineer more performance counter signals, like graphics counters for Fermi and Kepler, some MP counters, and all the work which can be done around performance counters with NVIDIA and Nouveau. So thank you. If you have some questions.
Yes, we want a demo of Nouveau.
No demo. Not yet.
Hi. I was curious to know if you considered the Linux perf infra as a way to forward the events to user space. So there's a perf event, OpenCL, the infrastructure that the user space perf tool is built on top of, which provides a way of forwarding events via a circular buffer. First, it's fairly CPU centric, so it's not necessarily a great fit for GPU performance counter forwarding, but I just wondered if you had considered it. And
I'm sorry?
Just wondered if you had considered that interface as an alternative, because you've made your own circular buffer model for forwarding events from kernel space.
Okay.
Okay, no, sorry.
The question is, est-ce que tu as pensé à perf?
Yes. Sorry.
Simple.
Yes, so this kernel interface will we should be able to expose performance counters with perf Linux, with perf only.
Okay.
Well, yeah, just one thing. The problem with perf is that it's CPU, it's synced to the CPU. So we may actually work to expose the performance counters, but synced to the CPU, so no frames or no anything. But it's just as a debug thing. It's not going to be very helpful to know exactly the number of vertices you rendered during this frame, which is very important too. So perf is not a perfect fit for every use case. But we are with the kernel interface, we could have a perf interface. So right now it's more oriented towards PerfKit because it's the most advanced one we have found for GPUs. But then, CPU is going to be interesting too when we want to.
Well, I'm asking because actually I'm working on very similar kinds of things for gen graphics, and in the way that I'm working at the moment, I'm experimenting with using perf as the way I forward events to user space. And I do have to work around some of the CPU-centric aspects of perf. It's not perfect, but not that tricky to make it work.
Yeah, I guess for clarification about the frame synchronization, we actually inject events into perf so that user space on the other side can reassemble everything. So you have the CPU, well, the global view and the per context, per draw view all in one stream.
I mean, in this case, I'm basically not expecting you to be forwarding any CPU-related information in that buffer. I'm not expecting you to want call stacks in your stream of events. Yeah.
Yeah. So essentially, even for the CPU, for the GPU-centric thing, we use perf as the transport protocol thing, and add a bit of. So that's kind of why it would be cool if you'd look into that too, because then we could do something.
It's pretty straightforward.
A bit, yeah, less hackish maybe, saner maybe too. That's useful for everyone.
Yeah, I guess we wanted to define an API that would work even for subframes inside a frame, just a block. You want what happens in a block inside a frame. Yeah, and so that's why we.
Yeah, I mean, we have similar requirements as well. I mean, I guess, so we also have an implementation of the AMD Performance Monitor extension and another extension, Intel Performance Query. But yeah, we're not dealing with the begin-end aspects in the kernel. We're just forwarding samples that are collected periodics. And from mesa, we have a separate mechanism where we're explicitly kind of marking the beginning and end of a query via the command streamer. So there's this kind of sideband information in our case, which gives us the timestamps at the beginning and end, which mesa collects via some commands that go through the command streamer, and then that's augmented with these periodic timestamps which come through perf. But it just kind of problem space, so I was just curious. But yeah.
Yeah, well, we've been talking with Daniel, and we agree that perf should be able to access the performance counters from Nouveau, so that's why we are actually interested in having most of the configuration inside the kernel. Yeah.
Thanks.
Very well. So, any other question? Thank you very much. Thank you, Samuel.
Thank you.